Ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about exceptions to the octet rule. So we've talked about Lewis dot structures, we've drawn lots of Lewis dot structures, and we've identified their geometries, but all of them have followed the octet rule. Now we're going to talk about elements that are above neon that don't follow the octet rule. In fact, even though we call them exceptions to the octet rule, a lot of these elements always are exceptions to the octet rule. So it ends up being more like, okay, the rules that we talked about work for very simple molecules and very simple things and ions. But then in reality, there's this whole other world of more complicated ones. So if you want to know why above neon? Why does it take beyond element number 10 to have, exceptions to the octet rule? The short answer that was always given to me was elements above neon have unfilled d orbitals that are only a few energy levels away that can be used for bonding. Now, if you say that to someone, that is completely disputed and is pretty much 100% inaccurate. So in reality, we really don't know why they are able to form these exceptions, but they do. That's all I can say, is that these exceptions occur readily when you go beyond neon. So maybe it's less an exception, then we should actually change the rule. We should say octet rule is just something that anything below 10 follows. And then if you go beyond, it's expanded. You have expanded octets, or sometimes what they're called. So the only difference when you're drawing something is that the central atom can have more than 8 electrons. The atoms that are on the outside, the outer atoms, can still only have 2 or 8. So there's still no exceptions for hydrogen. Hydrogen can only have a max of 2 still. And every other element, whatever you're bonding it with, can still only have 8. The only one that can have more than 8 is the central atom. And again, only if it is above number 10 on the periodic table. So this does seem to throw a wrench in one of our rules, though, right? So the problem would be this. We have our rules and we say, okay, follow these rules and you'll always get the right answer. And we always say that double and triple bonds are your last resort, right? If you can't get an octet, then you make a double or a triple bond. Now, the reason why this creates an issue for us is, picture this. We still follow the rules in order, no matter what. So even with the exceptions to the octet rule, we still follow the rules. But if, for example, let's say I'm adding dots to something like this. So let's say this is a nice expanded octet. Why can't I just add more indefinitely and make more double or triple bonds? So this is xenon tetrafluoride. So xenon, both of these structures have the exact same number of electrons. It's just one of them is right and actually exists, and the other doesn't really exist, or is unlikely, let's say, to exist. So but if you were to draw them and say, hey, I drew them, I have this right number of electrons, what's the problem? So there are a couple of problems, and we'll talk about what those are, but I'll just tell you that if you followed the rules in order, you would draw this. On the other hand, if you got to this point and you said, hey, it says that if, I want to have an octet, I can just kind of, make double or triple bonds somewhere. So what if I make these double bonds? Let's say I move my electron pairs in to the fluorines, and now I have 2 more double bonds like this. What's stopping me from doing that? So if you're following the rules, I could say, well, first of all, you're not following the rules in order. I could say that. The other thing I could say is, remember, only the central atom can have an expanded octet. So these fluorines have 10 electrons around them. They're also not following then the octet rule, which would immediately mean this structure would be incomplete and also just incorrect. But let's pretend that I'm comparing these two and I want to know which one's more likely to exist in nature. So here's how we do that. We check what's called the formal charge on the atoms. So the formal charge is just an informal way, even though it's called formal charge, of counting let's just say, quote unquote charge of each element. So remember, these aren't ions or anything. But let's say I wanted to calculate what the charge on this xenon would be and what the charge on this fluorine would be, and etc. I could do that. It's just not the way reality is, but I could totally calculate it. And so the goal, though, when you're looking at a Lewis dot structure to make it stable, is you want to have the lowest charges possible on all of your elements, okay? So for example, here is our formula for figuring out the formal charge. So the formal charge of something is equal to just the number of valence electrons on the atom minus the number of non-bonded electrons. These would be the lone pairs that you see. Those are non-bonded. And the number of bonds is just, the number of lines that you have. So let's figure out the formal charge of just a xenon in this, okay? So if I'm counting this, the formal charge would be, well, xenon has 8 valence electrons. So I'd plug in 8. I have 4 non-bonded electrons, 2 here and 2 here. And then I have 4 bonds. That means that xenon has an effective formal charge of 0. What about a fluorine, right? Fluorine is number, in the halogen group, its atomic number, I almost said. Its number is 7, though, for valence electrons. We're counting valence electrons. So I have 1, 2, 3, 4, 5, 6 non-bonded ones, plus 1 bond. That means that the fluorines all have a charge of 0. So what that means is this has a formal charge of 0, this has a formal charge of 0, and all of the other fluorines do. So this means this is totally stable. On the other hand, let's find out what that would be for this. So think about this. Again, valence electrons, xenon has 8. Non-bonded electrons, none. I have 0 non-bonded electrons here. How many bonds do I have though? 1, 2, 3, 4, 5, 6. So I would give 8 minus 6, that's 2 plus. That means the xenon has a formal charge of 2 plus. Now, for one fluorine, right, these 2 fluorines here, I have a charge of 0 just like before. But what about the ones with the double bonds? The ones with the double bonds have an effective nuclear charge of 1 minus. So picture this, right? I have 2 choices. I can have everything have 0 formal charge, or I could have this have a plus 2, and these have minus 1s to add up to an overall charge of 0. That means this is more likely to exist. This is less likely to exist because, again, look, the charges are separated. I have a 2 plus here, I have zeros here, I have minus 1s here. The charge is totally different. It's totally spread out compared to here where everything is the same. So that's how you would define or figure out, hey, is this the way this should actually look, or is it not the way it should look if you're comparing 2 structures to each other? Now, let's draw some Lewis dot structures using the steps that we just outlined. And we're going to calculate the formal charges on the elements. But for now, let's just kind of go with figuring out what the Lewis dot structure actually would be for these. So I have phosphorus pentachloride, right? So that means that you should attempt those ones. Now for geometries, these are our geometries. So these are our expanded geometries. Now, because they're expanded geometries, they all have very weird names. We have trigonal bipyramidal. Okay, that one sounds kind of like the other ones. Then you have sawhorse or seesaw. That one sounds totally weird. T-shaped, octahedral, square pyramid, and you can keep going. Now, remember, we said some of these geometries are polar, some of these geometries are non-polar. So let's add that to our list. So the blue ones, non-polar. Everything's balanced. Red, these are our polar shapes because everything is not balanced. Now remember, we're assuming that our central atom is something, and then our outer atoms are all the same element, whatever they might be. But this would give you a shortcut way of figuring out, hey, is this the way this should look? Is this actually the way it would exist? But again, just add that to your list. All right, so here's actually what you should have drawn for your actual, pictures. So phosphorus pentachloride would look like this. And then we have 5 bonds going to that. We have our outer electrons all with 8. In case you're wondering what the formal charges would be for this, the formal charge on this would be 0, 0, 0, 0, 0, and then phosphorus would be 0. So everything looks pretty good the way it is. Now, if I had to pick a shape for it, what would it be? It would be trigonal bipyramidal. And so the actual degrees are 120 and 90 degrees. And if you were to actually picture this, going along the center here, these would all be 120. These 2 facing up and down would be at 90-degree angles to one another. Sulfate is the one that no one really ever gets, okay? So sulfate, again, sulfur, it's beyond element 10, so sulfur could have an expanded octet. Most of the time, people draw them with just single bonds. So if you draw it with single bonds, let's calculate what the formal charge would be. So not on this one, but let's say you just made all of these single bonds. The oxygens would all be minus 1s. Sulfur would be a plus 2. So just like in our last example that we did on, a couple of slides ago, like the xenon tetrafluoride, you can see that that would be a pretty spread out charge. Now, what if instead you make these oxygens and sulfurs double bonds? If you do that, now here is the charge, okay? We've got, let's see. So you've got these ones here would be -1. These here would now be 0, okay? And sulfur would actually be 0. So you can see that it's an improvement. The sulfur doesn't have, like this +2. All these oxygens don't have -1s. Instead, now we just have 2 oxygens that have -1. And now if you're thinking, hey, is there a way to get everything to be 0? There's not. There's not a way to get sulfate to all be 0. And in fact, sulfate has a -2 charge because of the 2 non-bonded oxygens here. I said non-bonded. Because of these 2 single bonded oxygens here, that's the reason why it has a -2 charge. And then you can't really see here because, Screencastify, blast you Screencastify. The chlorines do have 8 electrons around them. They have 2, 4, and you can't see the 6 under here, and then this bond counts as 8. Same with this. You have 2, 4, 6, and then this bond counts as 8. So we have iodine trichloride. So again, if you're following your rules, let's say, everything would be balanced like this. So again, you'd have everything would be balanced, and you wouldn't have to make any double bonds. You wouldn't have to make any triple bonds. You wouldn't have to make anything like that. And the reasons for that are that if you find the formal charges for this, and if you try to make double or triple bonds and try to do anything crazy, the formal charges get out of control really, really fast. I guess I should have said sulfate doesn't, because it only has 4 things around it, it is just tetrahedral. It's not even one of the new geometries. That's how laid back sulfur is. It's just tetrahedral, 109 degrees, just like we did before. Now, iodine trichloride's shape is pretty weird. It has a T shape to it, and that means that its bond angles are just under 90 degrees. And so hopefully that helped. But if you have any questions, let me know, and I'll do my best to help you guys out.